I've been doing some work on black holes recently, which I hadn't started last time I saw you, actually. So I got interested in it. And the amount of the progress that's been made in trying to understand how they work. And a question that was posed by Stephen Hawking a long time ago, really 1970s, early 1980s, which is what happens to stuff that falls in. But the simplest question you could possibly ask.
Right.
There's progress being made on that now, which I think is profound and exciting.
How is the progress being made? Like, how do we study a black hole?
So we have two photographs, which are radio telescope photographs.
Right.
One of the one in the centre of our galaxy, which is a little one. It's called Sagittarius A star. It's a little supermassive black hole. So it's about 6 million times the mass of the sun, which makes it a little supermassive. And then there's another one, the first photo that was taken, it's a collaboration called Event Horizon. And they took a photo of one in the galaxy M87, 55 million light years away. That thing is around 6 billion times the mass of the sun. I mean, imagine that, 6,000 million times more massive than our sun.
Is that the largest black hole we've ever discovered?
No, there are bigger ones than that, but that's that's the scale of them. It's a big-ish one, that. But if you think about it, I mean, so there's a number, it's called the Schwarzschild radius of the thing. So if you took our sun, which you can fit 1 million Earths inside, and collapsed it down to make a black hole, it would form a black hole when it shrunk within a radius of 3 kilometres, about 2 miles. So you've got to take this thing, which is what I have to convert from kilometres to miles, don't I? But it's about...
That's okay, just say kilometres.
700,000 kilometres, so it's about 500,000 miles radius or something like that, the sun. So you squash it down till it's about 2 miles, and then that would form a black hole.
Wow.
The 6 billion times the mass of the sun means you multiply that by 6 billion. So these things, the so-called Schwarzschild radius is, I don't know, larger than our solar system, basically.
Oh
this
my
thing
God.
That sits in a galaxy. So we've got these two photographs.
Larger than our solar system.
Yeah, the event. Right. So it's a big structure there. That's the M87 black hole. So what you're seeing there is the emission from the material that's swirling around it. It's called the accretion disk. So you have material that's orbiting very fast, emitting a lot of radiation, and that's what you see. It's a flat disk, by the way. So you think Saturn's rings. So this material is very flat. And then just about, what was that, 4 years ago now, maybe 5 years ago, for the first time in history, we get an image of one.
How phenomenal is that?
Yeah. So we've had those two photographs. The other thing we've had is so-called gravitational wave detections. So these are colliding black holes, and they collide and merge together. And obviously that's quite a violent event in the universe. And so that event, that process ripples space-time. So it sends ripples out in the fabric of the universe. You get space and time. So really, actually, Kip Thorne, as we speak now, there will be these very tiny ripples from violent cosmic events passing through this room, and they're changing the rate that time passes, so that as they go through, and we can detect that now. So we have detectors that can pick that up, and so we've seen those collisions as well.
So these collisions, how far away?
Oh, millions of light years away.
And they're affecting what's happening in this room right now?
Yeah, to a tiny extent. So there's an experiment called LIGO. So basically it's laser beams. And there's one in Washington State, north of Seattle, and one in Louisiana. And they're kind of laser beams, 4 kilometre long laser beams at right angles. And they can detect these very tiny shifts. But it essentially measures the distortion in space-time caused by these ripples. God. And so we've observed many of those collisions. There it is. There's LIGO. So it's just basically 2 laser beams, but with these ultra high precision thing. And so we've got data now of the collision of black holes and those event horizon pictures with radio telescopes. In a sense, it was what's wrong with Stephen Hawking's calculation, which is a weird thing to say sometimes because people think Stephen Hawking surely didn't get his math wrong. But he did actually in his calculation. So what he calculated back in 1973, 1974 is that a black hole, so we picture this thing from which nothing can escape, even light. So when you go in, you're gone, basically. What he calculated is that even though these things are just a distortion in space and time, that's the description of them. So it's almost as if there's nothing there. apart from a distortion in space and time. He calculated that they glow, so they have a temperature, so they emit radiation. It's called Hawking radiation. And so important was that discovery. So he discovers these things glow, and he calculates how they glow. A very low temperature, but they emit things, which means that they shrink because they're emitting stuff, and so they're shrinking. So that means they have a lifetime. So first of all, one day they'll be gone. So that means that you have to address this question of what happened to all the stuff that fell in. And his calculation said that there's no record at all of anything that fell in all this radiation that's come off the black hole. So it's purely information-less radiation. So what that means is that black holes destroy information, according to that calculation. And that's a big deal because nowhere else in all of physics does anything erase information from the universe. So it's really true that if I got this notepad and pen, right, and I wrote some things on it, and then I set fire to this, even just incinerated it, put it in a nuclear explosion, whatever. In principle, according to all the laws of nature that we know, if you collected everything that came off, all the radiation, all the bits of ashes and things, and you could just measure it all, then just in principle, the idea is you could reconstruct the information. So it all gets scrambled up and thrown out and so in practice you can't do it. But in principle, the laws of nature say that information is not destroyed, it's just scrambled up in a way that you can't reconstruct, right? But this calculation that Stephen did said there is no information in that radiation at all. Zero, just nothing. So it seemed that uniquely in the universe, black holes erase information.